Hello and welcome to Power Systems 1 EEL 4213 FIU online course. Today we will cover module 4 part 2 of this module, since we covered part 1 that talks about the synchronous generator. In this part we will talk about the synchronous generator from different aspects such as its model parameters, the single operation of a synchronous generator, and the parallel operation of the synchronous generator. Then we will cover the characteristics of synchronous generator. Now let's start with the model parameters and talk about the quantities that describe the behavior of a real synchronous generator. These quantities range from the relationship between the field current and the flux, and therefore between the field current and the induced voltage. And if you remember, we talked about this in the previous part of this module, and the synchronous reactance and the armature resistance. In the following slides we will describe a simple technique for determining these quantities in a synchronous generator. Now let us remind ourselves what was the equivalent circuit for the synchronous generator from the previous part 1. So this represents here the equivalent circuit, the single phase equivalent circuit of a synchronous generator. Now in order to calculate the model parameters that we mentioned before in the previous slide, the first step is to perform the open circuit test on the generator. Now to perform this test, the generator is turned at the rated speed. Then the terminals are disconnected from all loads, and the field current here is set to 0. This is for the open circuit test. Okay, now then the field current is gradually increased in steps, and the terminal voltage is measured at each step along the way with the terminals open. Then IA, the armature current, equals to 0. Then based on that, EA will be equal to V phase. So it is possible to construct a plot of EA or VT, okay, versus what? Versus IF, because we are increasing gradually in steps the value of IF. Then based on that we measure the value of EA. So this plot is called the open circuit characteristic plot of a synchronous generator. With its characteristic, it is possible to find the internal generated voltage, which is EA of the generator, for any given field current. Now here we can see a typical open circuit characteristic represented by this figure. Notice that at first the curve is almost linear, then until some saturation is observed at the high field currents, as can be seen here. Now the unsaturated iron in the frame of the synchronous machine has a reluctance several thousand times lower than the air gap reluctance. So at first almost all the magnetic motive force is across the air gap, and the resulting flux increase is linear. Now when the iron finally saturates, the reluctance of the iron increases dramatically and the flux increases much more slowly, with an increase in the magnetomotive force. The linear portion here is called the air gap line, as can be shown here, of the characteristic. Now the second step in the process of determining the model parameters is to conduct the short circuit test. Now in this test we need to adjust the field current to 0 again, okay, and then we need to short circuit the terminals of the generator. through a set of ammeters, then the armature current IA or the line current IL is measured as the field current increases. So we measure IA as we increase IF. Now the figure here shows the short circuit characteristic of a synchronous generator. It's essentially a straight line, as can be seen here, and it represents a relation between the armature current and the field current, as we mentioned. Now, to understand why this characteristic is a straight line and it differs from the open circuit test, let us move to the next slide. Now, from the figure, when the terminals of the machine are short-circuited, as can be seen here, then the armature current is given by this equation here. It's EA divided by the impedance, the total impedance, which is RA plus GAXS. Now, the resulting phasor diagram is shown in figure B, and the corresponding magnetic fields are shown in figure C. Now, since BS is almost cancels BR, then the net magnetic field here is very small, corresponding to the internal resistive and inductive drops only. Now, since the net magnetic field of the machine is so small, this means that the machine is unsaturated. That's why the short circuit test characteristic is linear, and it does not have any nonlinear portion. Now, in order to find the XS, which is the synchronous reactance, we can use this equation where here ZS, which is the impedance, the magnitude of the impedance is the square root of 2 of RA square plus XS square, which is EA divided by the armature current IA. Now, since XS is much more greater than RA, then we can reduce this equation to XS equals to EA over IA, which is the same as V phase open circuit. Since in the open circuit test the V phase was equal to the EA divided by IA. Now, so an approximate method for determining the synchronous reactance XS at a given field current is first we need to get the internal generated voltage EA from the open circuit characteristic at that field current, then get the short circuit current flow, which is IA short circuit at the field current from the short circuit characteristic. Then at the end we find the synchronous reactance by applying this equation. So we found EA, we found IA, the first one from the open circuit characteristic and the second one from the short circuit characteristic. Then we can approximate the value of the synchronous reactance XS. Now, there is a problem with this approach that the internal generated voltage EA, as we saw here, it comes from the open circuit characteristic, where the machine is partially saturated for large field currents, as we saw in the open circuit characteristic curve, while IA is taken from the short circuit characteristic, where the machine is unsaturated for all field currents, as we saw before. It's always linear. Therefore, at higher field currents, the EA taken from the open circuit characteristic at a given field current is not the same as the EA at the same field current under the short circuit conditions. And this difference makes the resulting value of the synchronous reactance only an approximation. However, the answer given by this approach is accurate up to the point of saturation. So the unsaturated synchronous reactance of the machine can be found simply by applying the equation 2 at any field current in the linear portion or in the air gap line of the open circuit characteristic curve. The approximate value of the synchronous reactance varies with the degree of saturation of the open circuit characteristic. So the value of the synchronous reactance to be used um, should be when calculated at the approximate load on the machine. Now a sketch of the approximate synchronous reactance of a synchronous generator as a function of the field current, as can be shown here in the machine, is shown in the figure. Now the constant value of the reactance found at this part here is the unsaturated synchronous reactance of the machine. So let us write down here. So this part here represent the unsaturated, oops, okay, let's erase that. Okay, so this is the unsaturated XS. Okay, now what about the armature resistance? The resistance can be approximated by applying a DC voltage to the windings while the machine is stationary, then measure the resulting current flow. The use of DC voltage means that the reactance of the windings will be zero during the measurement process. Another parameter used to describe the synchronous generators is the short circuit ratio. This ratio is the ratio of the field current required for the rated voltage at open circuit to the field current required for the rated armature current at a short circuit. Now the short circuit ratio is just the reciprocal of the per unit value of the approximate saturated synchronous reactance. Now, although this ratio adds no new information about the generator that's not already known from the saturated synchronous reactance, it is important to know what it is, since the term is occasionally encountered in industry. So again, it is 1 over the XS. Now let us solve an example that talks about the model parameters. So we have a 200 kVA 480 volts and 50 hertz Y connected synchronous generator with a rated field current equals 5 amps was tested, and the following data were taken from the test. For the open circuit test, the V terminal or the V phase at the rated IF was measured to be 540 volts, and the IL at the short circuit or at the rated IF was found to be 300 amps. Now when a DC voltage of a 10 volt was applied to the two of the terminals, then a current of 25 amps was measured. So the question is asking us to find the values of the armature resistance and the approximate synchronous reactance in ohms that would be used in the generator model at the rated conditions. So let's start. Now the generator that we used is Y connected, and it was mentioned in the example. Since it's Y connected, so the direct current in the resistance test flows through two windings. So to calculate the armature resistance, we divide the DC, so we have 2RA equals to VDC over IDC, then VDC over 2IDC. VDC is 10 volts, is given in the question, and the resulting current is 25 amps, and then the RA will be 0.2 ohms. Now the internal generated voltage at the rated field current is equal to the V phase open circuit, and the V phase open circuit is the V terminal over square root 3, since the V terminal was given in the question, and we have Y connection. So based on that, the EA is 311.8 volts. Now for the short circuit current, IA, it's equal to the line current, since we have Y connection, so it's 300 amps, and it was given in the question. Now in order to find the synchronous reactance, we are gonna use the magnitude of the impedance, which is the square root of 2 for RA squared plus XS squared, which is EA divided by IA. Now we have found the value of RA and we know what's EA and IA. We calculated these two values. Then based on that we can find that XS equals to 1.02 ohms. Now how much was the effect of RA on the estimation of XS? So if we found that if we use that XS equals to EA over IA directly, then we can find that the value of XS is 1.04. so there is not much difference between 1.02 and 1.04, so the effect of RA on the estimation of XS is very small. Now the circuit here shows the per phase equivalent circuit for the generator in this example. This is the calculated value of RA, and here we have the XS, and here we have the EA value. Now the behavior of a synchronous generator under load varies depending on the power factor of the load and on whether the generator is operating alone or in parallel with other synchronous generators. We will begin our study for the behavior of synchronous generators with the synchronous generators operating alone, then we will move to the parallel operation. Here concepts will be illustrated with the simplified phasor diagrams, and we will ignore the effect of RA. As we saw in the previous example RA has a small effect. Then the speed of the generators will be assumed constant, and all the terminal characteristics are drawn assuming a constant speed. Also the rotor flux in the generators is assumed constant unless their field current is explicitly changed. Now let us understand the operating characteristics of a synchronous generator which is operating alone. Now an increase in the load is an increase in the real or the reactive power drawn from the generator. Such a load increases the load current drawn from the generator. Because the field resistor has not been changed, then the field current is constant, and therefore the flux is constant. Also, since the prime mover also keeps a constant speed, the omega, therefore the magnitude EA equals to K phi omega, and in this case it is constant. Now if EA is constant, then what does vary with a changing load? The way to find out this is to construct phasor diagrams, which we will see in the next slides, showing an increase in the load while keeping the constraints on the generator in our mind. The figure here shows the effect of an increase in the generator loads. Figure A, part A of the figure shows for a lagging power factor. So here we have lagging power factor, and here we have a constant or unity power factor, and here we have leading power factor. So here we can find that the current lags the voltage, and here the current equals the voltage, and same direction and the current here leads the voltage since it's leading power factor. So from the previous phasor diagrams we can notice three things. First, if we have lagging loads, so lagging power factor, that means the load is inductive. Then the V phase, you will notice that the V phase and the terminal voltage decreases significantly. So the generator before the load has the V phase and VT, and the generator after the load has V phase prime and VT prime, based on the phasor diagram that we saw in the previous slide. Now if we have a unity power factor loads, means there is no reactive power, then there is a slight decrease in the V phase and the terminal voltage. Now if we have leading loads, means we have a capacitive reactive power loads, then you will see that V phase and the terminal voltage will rise. Now, a convenient way to compare the voltage behavior of two generators is by using a quantity called the voltage regulation, which I think we discussed before. Now, for the voltage regulation is the V no load minus the V full load divided by the V full load multiplied by 100% because it's a percentage. Now, V no load represent the no load voltage of the generator, and V full load represent the full load voltage of the generator. And a synchronous generator operating at the lagging power factor has a fairly large positive voltage regulation, while synchronous generator operating at a unity power factor has small positive voltage regulation, and if the synchronous generator is operating at a leading power factor, then it will often has a negative voltage regulation. Normally, it is desirable to keep the voltage supplied to a load constant, even though the load itself varies. So how can the terminal voltage variations be corrected? We can use an approach by varying the magnitude of EA to compensate for the changes in the load. So in order to do that, we can first decrease the field resistance in the generator, and this will increase its field current. Then an increase in the field current will increase the flux in the machine, while the flux in the machine will increase the internal generated voltage, which is EA. And an increase in the internal generated voltage will increase the phase and the terminal voltage of the generator. Now let us solve an example that discusses the terminal voltage variations and how it can be adjusted. So this example shows that we have 480 volts 60 hertz connected 4-pole synchronous generator that has the open circuit characteristic, which we'll see in the next slide. This generator has a synchronous reactance which is XS equals to 0.1 ohms, and with armature resistance equals to 0.015 ohms. Now at full load, this machine supplies 1200 amps at 0.8 power factor, and it's lagging. Okay, so it's inductive load. Now under full load conditions, the friction and the windage losses are considered to be 40 kilowatts, and the core losses is considered to be 30 kilowatts, and says to ignore any field current losses. So here we can see the open circuit characteristic of this example for the machine in this example. Now the question is asking us to find several things. First, they want us to find what is the speed of rotation of this generator, then how much field current must be supplied to the generator to make the terminal voltage 480 volts at the no load, and if the generator is now connected to a load and the load draws 1200 amps at 0.8 power factor lagging, as we saw in the example, then how much field current will be required also to keep the terminal voltage equal to 480 volts. Also, how much power is the generator now supplying, and how much power is supplied to the generator by the prime mover, and what is the machine efficiency. Now, if the generator's load were suddenly disconnected from the line, what would happen to its terminal voltage? Then at the end, suppose that the generator is connected to a load that's drawing 1200 amps with 0.8 power factor leading, means it's a capacitive load this time. Then how much field current would be required to keep the terminal voltage again at 480 volts. Now, this synchronous generator is delta connected this time, so in this case we know that the relation that between the phase voltage and the line voltage that they are equal, so V phase will be equal to V line or V terminal, and the phase current is related to the line current by the equation IL equals square root 3 of I phase. Now the relationship between the electrical frequency produced by the synchronous generator and the mechanical rate of the shaft rotation is given by this equation, which we explained I think in part 1 of this module. So in order to find the speed of rotation, the mechanical speed of rotation, it's 120 multiplied by the electrical frequency divided by the number of poles. We have 60 Hz frequency and 4 poles. This will give us 1800 revolution per minute. Now in this machine we said that the V terminal equals to V phase. Since the generator is at the no load, then the armature current equals to 0, and based on that the induced voltage, internal induced voltage, equals to V phase. And since the V terminal equals to V phase equals to the internal generated voltage, so we have it equal to 480 volts. And from the open circuit characteristic, if you refer to the figure that I showed in the previous slide, you will find that at 480 volts we will have field current of 4.5 amps. Now for part C of this question, if the generator is supplying 1200 amps load, then the armature current in the machine will be the 1200 amps divided by square root of 3 because the armature current represents phase current, okay, and we have delta connected generator, so based on that it's 692.8 amps. It was given in the question that the power factor is 0.8 power factor lagging, so based on that we can find the angle, which is minus 36.8 7 degrees for the armature current, and this is the magnitude that we calculated in the previous slide. Now if the terminal voltage is adjusted to be 480 volts, then the size of the internal generated voltage will be given using this equation. We change the terminal voltage to 480 with angle 0 degrees, and we calculated the value. We know the value of RA, we calculated IA, and XS here is given. So by the end we will have that to keep the terminal voltage at 480 volts, then the internal voltage must be adjusted to 532 volts from the figure in slide 24, I guess 24, okay, which is the open circuit characteristic figure. Then the required field current from this figure at this voltage, we can find it to be 5.7 amps. Now what about the power that the generator is now supplying? It can be found using this relation. P out is square root of 3 multiplied by V line, I line, cosine theta. So what is theta, I line, and V line? V line is the 480 volts, and the I line is the 1200 amps for our load, and the angle is which is 36.87 degrees. This will give us that the output power is 798 kilowatts. Now in order to determine the power input to the generator, we use the power flow diagram that we discussed in part 1 of this module. We know that the P input is the summation of P output plus the losses. In the losses we have the electrical losses, the core losses, the mechanical losses, and the stray losses. Since the stray losses were not given in the example, then we will ignore it. The electrical losses can be calculated using this expression, 3I A squared RA. IA is the armature current calculated, which is the 692.8 amps, and RA is the 0.015 ohms. This will give us electrical losses of 21.6 kilowatts. The core losses were given in the question 30 kilowatt. Friction and windage were given also in the question 40 kilowatts. So in general, the total input power to the generator is the summation of all of these losses plus the output power, which will give you 889.6 kilowatts. So efficiency is the output power divided by the input power, and it will give us 89.75% efficiency for this generator. Now if the generator's load were suddenly disconnected from the line, then the armature current would drop to 0, making the induced voltage in the generator equals to the phase voltage. Now since the field current has not changed, then the magnitude of the induced voltage has not changed, and the V phase and V terminal must rise to equal the induced voltage. Therefore, if the load were suddenly dropped, then the terminal voltage of the generator would rise to 532 volts that we calculated in part C of this example. If the generator were loaded, but this time with the 1200 amps and 0.8 power factor leading, while the terminal voltage was 480 volts, then the internal generated voltage here, we will change the, in this case, the IA angle to a leading angle, and this will give you 451 with angle 7.1 degrees for the internal voltage. So with a leading power factor, the internal generated voltage must be adjusted to provide 451 volts in order to make the terminal voltage remain at 480 volts. Now if you use again the open circuit characteristic figure that we saw before, this will give us a field current of 4.1 amps. Now after we talk about the single operation of the synchronous generator, we will move to the parallel operation, and we will say that for all usual generator applications, there is more than one generator operating in parallel in order to supply the power demanded by the loads. An extreme example for that is the situation in the US power grid, in which we have thousands of generators that share the load on the system. So why synchronous generators can be operated in parallel or need to be operating in parallel? Several generators can supply a bigger load than one machine itself, and having many generators increases the reliability of the power system, since the failure of any one of them does not cause a total power loss to the load. Having many generators also operating in parallel allows one or more of them to be removed for shutdown and preventive maintenance. If only one generator is used and it is not operating at full load, then it will be relatively inefficient. So with several smaller machines in parallel, it's possible to operate only a fraction of them. Now the figure here shows a synchronous generator G1 supplying power to this load. Then we have another generator, which is the G2. It's about to be parallel with the G1 by closing the switch S1. Now let us ask ourselves a question: what conditions that can be met before the switch can be closed, switch S1 can be closed, and the two generators are then can be connected? The conditions are as follows. The RMS line voltages of the two generators must be equal. The two generators must have the same phase sequence, and the phase angles of the two phases must be equal, and the frequency of the new generator, which is called the oncoming generator, must be slightly higher than the frequency of the running system. Now you will see this in the next slide. I will ask you to watch a YouTube video. Then after that you will answer several questions and that are related to these conditions, and this will explain to you why these conditions need to be met before connecting these generators in parallel. Now let's talk a little bit about the characteristics of synchronous generators. The prime mover is the generator's source of mechanical power. The most common type of prime movers is a steam turbine, but the other types include diesel generator engines. We have gas turbines, water turbines, and we have also wind turbines. Now, regardless of the original power source, all prime movers tend to behave in similar fashion. So as the power drawn from them increases, the speed at which they turn decreases. Now the decrease in the speed is in general non-linear, but some form of governor mechanism is usually included in order to make the decrease in speed linear with an increase in the power demand. Now whatever governor mechanism is present on a prime mover, it will always be adjusted to provide a slight drooping characteristic with the increase in the load. So how can we calculate the speed droop, which is abbreviated by SD? of the prime mover. It's actually the no load prime mover speed minus the full load prime mover speed divided by the full load prime mover speed. Now most generator prime movers have a speed drop between 2 to 4%, and most the governors have some type of set point adjustment to allow the no load speed of the turbine to be varied. Here figure A shows the speed versus the power curve for a typical prime mover, and in this figure we can see the resulting frequency versus the power curve for the generator. Now the relationship between the frequency and the power that we saw in the previous figure, figure B, can be described quantitatively by this expression. We have P equal to SP multiplied by the F no load minus the F system. P represent the power output of the generator, and the F no load represent the no load frequency of the generator, while the operating frequency of the system is represented by F system, and SP represent the slope of the curve in kilowatt per hertz or megawatt per hertz. Now let us solve an example that discuss the characteristics of the synchronous generator and also kind of having different loads connected to it. The figure in the next slide shows a generator that supplies a load. A second load is to be connected in parallel with the first load. Now the generator has a no load frequency of 61 Hz and with a slope of 1 megawatt per hertz. Load 1 consumes a real power of 1000 kilowatt with 0.8 power factor lagging, and the load 2 consumes a real power with 800 kilowatt and 0.7 power factor lagging. Now before the switch is closed, what is the operating frequency of the system? Then after the load 2 is connected, what is the operating frequency of the system? And the last part of the question is, after the load 2 is connected, what action could an operator take in order to restore the system frequency to 60 Hz? So here we can see the generator that supplies the two loads. So let's start solving this example. This problem states that the slope of the generator characteristic is 1 megawatt per hertz and the no load frequency is 61 hertz. Therefore, the power produced by the generator, we know this expression, so we need to know the system frequency. So it's gonna be F no load minus P over SP. And now the initial system frequency will be 61 Hz for no load frequency minus 1000 kilowatt for the first load divided by 1 megawatt per hertz. This will give you 60 Hz, okay, for the system frequency. Now after load 2 is connected, the total power supplied by the generator will be 1800 kilowatt, because for the first load is 1000 and for the second load is 800, so we took the summation. So based on that, we will get that the system frequency has decreased to 59.2 Hz. So what is the solution for that? For the fall that occurred in the system frequency, the operator should increase the governor no load set points by 0.8 Hz, so it will be 61.8 Hz. This action will restore the system frequency to 60 Hz. So to summarize, when a generator is operating by itself, supplying the system loads, then the real and reactive power supplied by the generator will be the amount demanded by the attached load. Also, the governor set points of the generator will control the operating frequency of the power system, and the field current or the field regulator set points controls the terminal voltage of the power system. So this is the situation found in isolated generators in remote field environments. So by that we can say that we completed the module 5 of this course, and in this module we derived the characteristics of a synchronous machine from measurements using the open circuit characteristic and short circuit characteristic. Also, we described how the terminal voltage varies with the load in a synchronous generator operating alone, and we discussed the terminal voltage at very slow conditions. Then we identified the conditions that are required to parallel 2 or more of the synchronous generators. At the end, we explained the procedure for paralleling the synchronous generators. Thank you so much for listening and watching. And the homework 4 will be based on after module 6. So we will not have homework 4 after this week. It will be next week. So thank you again, and please review your book and the other resources that I posted during the lecture video, and good luck in the remaining part of this course.